In this video, this is our second of 3 quick factoring review videos. We're going to talk about factoring quadratics. So, a couple of things to say about a quadratic. So, what is a quadratic? A quadratic is a polynomial of degree 2. So, in its most generic form, it looks like ax squared plus bx plus c. So I want to go back to something that we mentioned in the greatest common factor video, which is the whole idea of degree. So because the highest term here has degree 2, the whole polynomial is degree 2. And why is this so important? Because it means that if a quadratic polynomial factors, it has to factor into either a degree 0 factor, so a constant, and then a degree 2 factor, so a quadratic, or 2 degree 1 polynomials, or 2 degree 1 polynomials and a degree 0 polynomial like a constant. So it's really important to kind of be thinking about that as you are factoring a quadratic. So real quick, before we jump into some examples, here A, B, and C are called the coefficients. And A here is called the leading coefficient. We could give B and C names also, but it's actually not terribly important to do that right now. The reason that I want to spend a moment on A is that if A is 1, our life gets significantly easier. So let me show you an example, and then we'll go from there. So I'm going to take a totally trial and error approach to this, and we're going to build a technique out of our trial and error approach. Okay, so for example, let's factor x squared minus 4x minus 5, okay? Okay, so this is a degree 2 polynomial. So the first thing we want to do, and this goes back again to our video from last time, what is the GCF? So you'll notice actually, if you're watching closely, that I started writing the word is, like, is there a GCF? Well, in fact, that's not the right question to ask because there's always a GCF. And I'm going to write that here. There is always a GCF. Both plus and minus 1 are always GCFs. The thing is, if that's all there is, we often ignore it, unless it's -1, in which case we pull out the negative, and we'll talk about that in a later example, in fact, in our next video. So if the GCF is just 1, we basically leave it alone. We don't bother with it. Agree with me, right, that everything is divisible by 1. So everything always has that common factor. So we don't think about it too much, but it's important to acknowledge that it's always there. So looking at these things, x squared, negative 4x, and negative 5. Well, they don't all have an x in them, so the greatest common factor doesn't have an x in. And then the coefficients, well, x squared is by itself, so that means its coefficient is 1. And then the other coefficients are -4 and -5, which don't have any common factors. So in fact, the GCF is just 1. So we're not going to bother factoring it out. It doesn't actually break the polynomial down any further. What this tells us is that if this polynomial factors, and yes, I said if, and we'll talk about that in a second, if this polynomial factors, it's into 2 degree 1, aka linear, factors. So this kind of detective work is really good to do before you actually start down the rabbit hole of like, how do you factor? So, okay, so here we go. And the beauty of this software is that it's very easy to erase things if they turn out not to work. So here goes. We know that if this factors, there are two linear factors. Okay, so what is a linear factor? It has an x term and it has a constant term. So let's start by talking about the x terms. Could I have 2x here and like 3x here? Like, could that work? Well, what do you think? I think not, because if I have a 2x and a 3x, they multiply to 6x squared. And that's not what we have. We have x squared. And the whole idea of factoring is that you're rewriting your original polynomial, but in this new form. So that doesn't work. So it's not 2x and 3x. And not only does it not work, and this is one of the things that if we were face to face, you'd hear me and see my face say this at least a million times. Failing is important because oftentimes by failing, we figure out what would have worked. So failure is key to the learning process. Never tell anybody that learning cannot involve failing, that you cannot fail. You must fail to learn. So since those two x terms have to multiply to x squared, there's really only one thing they can be, and that's x and x. Okay. Now let's talk about the constant terms, right? So linear polynomials or linear factors only have those two terms to speak of, the x term and the constant term. So just for the sake of argument, let's say that, I don't know, I have like plus 7 and minus 4, okay? So does that work? Well, what do you think? Much the same way that we determined that 2x and 3x won't work because they do not multiply to x squared, I have exactly the same problem with 7 and negative 4. They multiply to negative 28. So the polynomial that you would get if you multiplied this back out would have a minus 28 on the end, and our polynomial doesn't. So for sure, this doesn't work. It cannot be plus 7 and minus 4. But just like before, not only did we see that something didn't work, we also learned about what it needs in order to work. We need these two constants to multiply to negative 5. Okay, so what multiplies to negative 5? Well, it turns out there's more than one way to multiply to negative 5. You could have plus 5 and minus 1. Or you could have minus 5 and plus 1. So does either one of them work? Well, so now what many of you will notice is we've talked about the x squared term, we've talked about the constant term, but we've sort of been ignoring that middle term, that x term. Well, as it turns out, the middle term gets the last laugh because the middle term is the one that will eventually decide whether your factorization is accurate. So let's see. If I have x plus 5 times x minus 1, and I were to distribute that out, remember distributing means everybody gets multiplied by everybody. We can draw a picture about this, and we probably will in future lessons, but for now we'll make it quick. Well, my x terms are going to come from multiplying the x terms by the constant terms. So I have plus 5x from multiplying up here, and minus x from multiplying there. Does that give me the minus 4x that I'm supposed to end up with? Nope. If I have positive 5x and negative x, that gives me positive 4x. So in fact, this is not the correct factorization. But what's really good is that by seeing that something doesn't work, I also learn what would have worked. X minus 5 times x plus 1. We're feeling pretty good about it, right? Because it literally fixes the problem that the other version had. But my advice to you is, because sometimes feelings and intuition are not quite on the money, we're building them up to be better. That's one of the things we're doing in this class is we're building up mathematical intuition. But always check your work to help you in constructing that intuition. So here we go. Let's check. Check your factorization. So if in fact we factored correctly, then if I multiply x minus 5 by x plus 1, I should get x squared minus 4x minus 5. So here goes. X minus 5 times x plus 1. I'm distributing through. I like to use arrows. I also like to use pictures, but there's more than one way to do it. So we have x squared plus x minus 5x minus 5. So this actually gives us a very convenient opportunity to remind ourselves that these two are called like terms, x and negative 5x. So we can combine like terms. And since we have 1x minus 5x, that turns out to be minus 4x. So yes, in fact, the factorization is accurate. I cannot stress the importance of checking your factorization because sometimes you'll feel in your heart of hearts that you've got it and that it's right. But then you look a little bit more closely and you realize, you know what, that doesn't pan out. Okay, next. So let's try this example. So we'll look at a simple example with a leading coefficient that's not 1 this time. So let's look at 2x squared plus 5x minus 7. So again, you'll remember a is our leading coefficient. Our first example, a was 1. And I mentioned when a is 1, you'll notice things are much easier and things go faster. When a is not 1, like in this case, a is 2, it's a little bit more involved and you sort of have more balls in the air and you just have to pay closer attention. But in spirit, like the substance of the matter is the same. You still have to pay attention to all of the same things and you still have to be careful in all the same ways. The thing that makes this example nice or perhaps a little easier is that both your leading coefficient 2 and 7 are both prime. And that's always, like, whenever you see that, you kind of smile to yourself because prime numbers don't break up much. They don't break down in any way except themselves times 1. So that means that as far as options go, there aren't going to be very many options. So if this factors, there aren't going to be too many options for it. I'm not going to write it all out again, but once again, we're going to ask the question, what is the GCF? And we again are going to notice that, well, the three terms don't all share an x, and 2, 5, and negative 7 are relatively prime. They don't share any factors. So the GCF is 1, so we're not going to worry about it. Okay, so I'm going to start right in, and I'm going to say since the GCF is 1, and I'm not going to make a special, process for it. This is going to factor, if it factors, into 2 linear factors, just like the first one. Now, I hope to kind of gain some ground based on the lessons I learned from my previous example. So I know that linear factors have an x term and a constant term, and I know that the two x terms have to multiply to 2x squared. So the only way to multiply to 2x squared is 2x times x. This is where the fact that 2 is prime comes in handy. If it was like 6x squared, then we would have had to think about something like 2x and 3x or x and 6x. But because it's 2x squared, there's only the 1. Now, when we look at the negative 7, well, again, it's nice because there's not very many ways to multiply up to negative 7. There's positive 7 and negative 1, or there's negative 7 and positive 1. So let's just, for the sake of argument, put the positive 7 here and the negative 1 here. So this is where you see why the fact that the leading coefficient is not 1 makes things a little bit more difficult. It is going to impact who gets multiplied by the 2x, right? In the last example we did over here, both of the linear factors led with an x. So we didn't need to check, oh, well, would I put the -5 in the left column or in the left factor or in the right factor? It didn't matter because it would all multiply out the same because the other term was x in both cases. Here, the x term is different. So we not only, to rule out +7 and -1, we have to try +7 with the x, -1 with the 2x, and vice versa. So in fact, the 2 being there as the leading coefficient, it increases the number of possibilities that we could have. Okay, so here goes. Does this work? We'll put a question mark. So we have 2x times 7. Now what many of you are going to start to have is kind of a gut feeling, like, oh, this doesn't look good. Because you know that you want to end up with 5x in the end. And the 14 is too big, right? There's not enough, the -1 and the x don't pack enough of a punch to bring the 14 down to 5. So as soon as we see the 14, many of us probably got a sinking feeling like, oh man, I don't think this is going to work. But again, right, as I said a few moments ago, we did not just rule out +7 and -1 because we still have to try the +7 where the -1 was and the -1 where the +7 was. So let's try it. Right, so it takes more checking to rule out. Okay, so here we go. So does this work? So we have 2x times -1, that's -2x. So again, kind of tap into your feelings here. Many of you will probably feel like sort of a good feeling in your brain, like, oh, this is going to work. I have 7x and -2x. Sure enough, those combine to +2x. Now, some of you might be thinking, ugh, this is so tedious, but it's actually one of those things that gets easier as you practice because you start to develop a better sense of intuition. So yes, not only do we know this works, but we actually also already did the checking. Okay, so let's do one last example, okay? And as I said in the beginning of this lesson, and as I will repeat many times, factoring is something that it takes a little practice. Many of you are going to struggle with it, and many of you are going to need review, but we're just going to keep reviewing it when we get opportunities to do that. So don't feel like this factoring quadratics video is going to make you super 100% comfortable with factoring. Okay, so for our next example, we are going to look at 4x squared plus 8x minus 5. Okay? So, again, the leading coefficient is not 1, it is 4. And it's also not prime. So we're just kind of turning up the volume with each example. Each example is a little bit more interesting than the one that came before it. The good news is the constant is still prime, so we're not going to have a ton of options. Now, one thing that I've been saying, and I'm going to do one last example after this to show you, is if a quadratic factors. A quadratic is not obligated to factor at all. It could have a GCF of 1, and it could be not possible to break down beyond that. So don't allow yourself to believe that every single quadratic out there factors neatly into 2 degree 1 polynomials. The ones that we interact with will a lot of the time, but not all the time. So it's important to kind of have that in the back of your head that this might not work, and that's okay. All right, so here we go. We're going to assume that this factors into 2 degree 1 factors. So I'm going to skip a little bit of all of the exhaustive steps just to save time. But I want to show you that the x terms, right, this is two linear factors, the x terms have to multiply to 4x squared, which means that it could be 4x and x, or it could be 2x and 2x. Where you start trying is totally your call, but I'm going to start with 4x and x, and I'm not going to go all the way through it. I'll kind of skip to the punchline after a try. Now, the minus 5, that's prime, thank goodness. So let's just, for the sake of argument, say that it's 4x plus 5 times x minus 1. Notice that that achieves the 4x squared in the front and the minus 5 in the constant term. So as before, the middle term has the last laugh. It's all about, does the middle term does the x term come out to be positive 8x? So let's see what we got here. So we have 4x times negative 1 and 5 times x. I'm not even going to write them out because it's not looking good, right? 4x times negative 1 is negative 4x. And then 5 times x is positive 5x. That doesn't come anywhere near 8x. Now, you could continue trying, right? So this didn't rule out plus 5 and negative 1. You could also try the plus 5 in the other term and the minus 1 with the 4x. You could try that. And then just because plus 5 and minus 1 didn't work doesn't mean plus 1 and minus 5 didn't work. And I actually encourage you to try them, because one of the things that you will see if you try is that very quickly it becomes obvious that the 4x and x scenario just doesn't pan out. The numbers are either too close together to make the plus 8x, or they're way too far apart to bring back to 8x. So the 4x and x configuration doesn't work. So we're going to skip to trying 2x and 2x. Now, I'm sort of spoiling it here because I'm sort of promising you that this will factor. But you should keep in mind that it doesn't always. So again, the 2x and the 2x multiply to 4x squared. The constants should multiply to negative 5. And then, of course, the x terms should add to 8x. What I'm kind of hoping is that some of you are starting to feel the rhythm of this a little bit, and some of you are already starting to see how this is going to go. But I'm going to do one wrong example just to show you. So let's say that we have plus 1 and minus 5. So if you have plus 1 and minus 5, you have 2x times negative 5 is 10x. You have 1 times 2x is 2x. Oh, so close. They make an 8, but they make a negative 8 when we wanted a positive 8. Now, what I'm kind of hoping is that you all are sitting here thinking, oh, but because both of the x terms are 2x, I don't need to do that whole thing where I switch them around. So once you saw that plus 1 and minus 5 didn't work, you don't need to try the plus 1 in the other and the minus 5 in the other, because both of the x terms are 2x, so it won't change anything to do that. So let's try plus 5 here and minus 1 here. Sure enough, if we check it, 2x times minus 1 is negative 2x. And 5 times 2x is positive 10x. And so then when we combine those, we get positive 8x. So sure enough, this works out. I'm going to use this opportunity to remind you. So remember, multiplication is commutative. And what that means is that you can write a product in any order you want, commutative. So you could write 4x squared plus 8x minus 5 is equal to 2x plus 5 times 2x minus 1. Or you could write it 2x minus 1 times 2x plus 5. Either way is fine. Multiplying in the opposite order does not change the value of the product. So as I promised, I want to show you one last example. In this example, I'm actually not going to do all the way through. I'm going to leave it as a see for yourself. I'm going to tell you the punchline, and then I'm going to ask you to explore. So 3x squared minus 7x plus 1. What I'm going to tell you is this is a perfectly lovely quadratic, and it's prime. Meaning that it is not possible to meaningfully break it down any further. The only way to break it down is 1 times itself or -1 times the opposite of itself. So play around with it, kind of using the techniques that we use in the rest of the lesson. Play around with it, see if you can come to that conclusion, see if you believe it. If you don't believe it, ask me about it. All right, that's all I got for you. See you later. Bye.